All right, now I would like to look at the problem of hydraulic jump from energy perspective. In the previous video, what we did, we looked at the energy at a specific point on upstream and downstream. Now I can use control volume analysis for energy to actually calculate how much heat is generated inside this hydraulic jump, or how much extra energy is generated accurately. All right, so let's just start with the schematic of the problem. Let's just get this one to work. All right, this is our surface. This is the stream, and then complications and outlet velocity. So the inlet velocity is V1, height of the inlet stream is H1, and then the outlet velocity is V2. We assume it's uniform, and the height of the outlet velocity is H2. I'm going to pick a control volume about the jump, just to jump, hydraulic jump, so that we can neglect the effect of skin friction, viscosity of the wall. And I'm going to bring the values of V1 and H, the relationship between V1 and H1 and H2 from the momentum equation here. Now I would like to move on and write down the energy equation. So that is d dt of integral of E rho d volume plus integral over control surface, this is over control volume, of rho E plus P over rho V dot n hat dA, that is equal to Q dot in plus W dot shaft. All right, it's a steady state problem. We assume it's isothermal, but no temperature increase or decrease. So therefore, the first term is 0. Also remember that E is the intensive property for energy. So that is equal to U tilde, which is a measure of internal energy, plus kinetic energy plus potential energy. Now, I can argue that the contribution of internal energy for this problem is 0 because it's an isothermal problem. And the reason is because of conservation of mass. Whatever mass that enters control volume, our control volume leaves our control volume. And therefore, because it's an isothermal and incompressible, the amount of energy that comes with the mass to the control volume is equal to the amount of energy that leaves control volume. So the overall contribution of U tilde is 0. Okay, so I'm going to proceed with assuming U tilde doesn't have any effect. I've set it equal to 0. If you're in any doubt, just write it down, take it into account, and you're going to see that it's going to just cancel out from both sides of the equations. All right, so the contribution of control surface integral, i.e. the second integral, this integral, is over the surface 1 and surface 2. Okay, so let's first calculate the contribution of this integral over surface 1. That's going to be integral over control surface of rho. Now I decided to, I argued that U tilde doesn't have any effect, so I'm not going to consider that. 1/2 V1 to the power 2 plus GZ, all right, plus P over rho. Now what is P? Pressure is hydrostatic, so if this is my X, this is my Z, it's easy to see that pressure is rho G, and it's going to be H1 minus Z, because now at Z equal to 0, the pressure is rho G H1, at Z equal to H1, pressure is 0. So therefore, the pressure term here, this P over rho, and if I divide that expression to rho, I get G times H1 minus Z. All right. And there you go. I'm going to substitute this parentheses with a bracket. All right, and V dot N for the area 1, V dot N, V is to the right, N hat is to the left. So V dot N gives me negative V1. And dA is B, which is the width of the control volume, times dZ. All right, now interestingly, this G minus Z, so this is going to be GH1 minus GZ, GH1 minus GZ, and this minus GZ cancels out this GZ, all right? And I'm going to left with rho 1/2 V1 to the power 2 plus gh1, and this is just 1, times negative v1 times b, and then the integral of dz going from 0 to h1 dz just gives me h1. So this integral is going to be equal to minus rho 1/2 v1 to the power 2 plus g plus gh1 v1 bh1. All right, and if you do the same integration for area 2, this is going to be the negative sign becomes positive rho 1/2 v2 to the power 2 plus gh2 v2 b and h2. All right, so all we need to do is just basically add the two integral together. So 1 plus 2, 1 plus 2 gives me, and I can factor out rho. Remember also from conservation of mass, v1 h1 is equal to v2 h2. So v1 h1 I can factor out, and b is of course the same thing. So therefore it becomes 1/2 v2 to the power 2 minus v1 to the power 2 plus g times h2 minus h1. So now what I can do, and again from conservation of mass, this is our left hand side. All right, so I can just put this here. Let's just move this a little bit to the right. So this is the left hand side, and actually I can just write down everything. We don't have a w dot shaft, so this is equal to the q dot in. Now with the conservation of mass, there's a relationship between v1 and v2. Write it down. So conservation of mass, we have v1 h1 is equal to v2 h2. So I can get rid of v2 in the expression above. I'm going to have rho v1 h1 b times 1/2 v1 2. All right, and instead of v2 I can put v1 h1 over h2 to the power 2 minus 1. All right, and this turns into a curly bracket. All right, plus g h2 minus h1 is equal to curly bracket here, q dot in. All right, now what I'm going to do, I'm going to use the expression that we have for v1. I'm going to just copy paste this here. Copy and bring it here. Paste. There you go. So therefore, I can write this as rho v1 h1 b 1/2 v1 to the power 2 is going to be 1/4 of g h2 over h1 times h1 plus h2, and then this has to be multiplied by h12 minus h22 divided by h22. All right, plus g times h2 minus h1. That's q dot in. All right, now let's see what kind of simplifications we can make. I can take out h1 and h2 out of curly brackets, so I have rho v1 h1b times h2 minus h1. Now h2 cancels with 1 power of h2 here, and then there's going to be h1 plus h2. So this term I'm actually writing it as h1 minus h2 that I took out of the parentheses times h1 plus h2. And the second term, like this term and this term together, make a h1 plus h2 to the power 2. So therefore, what I'm going to have is h1 plus h2 to the power 2. All right. I can also take out g. So this g, let's put it here. All right. And what I'm left with is there's going to be a 4 h1 h2 in denominator plus there's going to be a minus here and then plus 1. The reason I have a minus here is I'm taking out h2 minus h1, but the first term has h1 minus h2. So if I factor out h2 minus h1, I have to leave a minus sign that appears here. All right, and that's it. I think all terms have been taken care of. That's q dot in. And then so we have rho g v1 h1 b h2 minus h1. This is going to be minus h1 minus h2 to the power 2 divided by 4 h1 h2. That's q dot in. So we calculated as a function of h1 and h2 what exactly is the heat that has to basically leave our system. And because h2, remember h2 is greater than h1, that's what we got to have a hydraulic jump. And the quantity inside this parenthesis is negative, everything outside is positive. So therefore q dot in is negative, which means that basically energy is leaving control volume. And basically we have the exact expression for how much energy is in fact leaving the control volume. Let me draw a box about it, and there you go.